I forgot why it's an R, but it's the value that the direct utility that the consumer gets from the product. And it comes from like the word. I can't remember what it is. This is the book.
Yeah, the one is like the thing.
I can check it on the book. ¿Está en el libro?
I don't know.
No, we don't know.
I mean, the model sounds good, but I don't know if you have like some reason why it's called R. Yeah, R is the reservation value.
Yeah, that was
Okay, it's the willingness to pay, and the willingness to pay sometimes is called reservation value. Okay, because it's the maximum price that you will be willing to pay for the product, and in this case it's absent also in any transportation costs. Okay, it's the value of the product that you will be willing to pay the most. It's the willingness to pay, including price and transportation costs. Okay, you're paying in two ways.
Reservation value.
So it's willingness to pay including transportation costs.
Okay, so I said that this model is not very well behaved. I'm going to see why. So far everything was really nice, but then unfortunately it leads to discontinuity in the demands, and we'll see why. Suppose we were to plot the utility, right, that the consumers get from buying from firm 1 or from firm 2. Okay, so this is the utility here. Okay, and what's the utility if the firm is located at L1 and that's the price of P1? For the person that's here, it's going to be the transportation cost is 0, so here is going to be R minus P1. Okay? The person, for the consumer that's located exactly where the firm is located, right? We live next door to a grocery store. It's the reservation utility, the reservation value, R, how much you're willing to pay, absent price and transportation cost, minus the price. And for the others, there's going to be a slope. It's going to be linear, right? The utility, you got to do tau times x minus L1. So it's going to have slope tau. That's going to increase with x as you get further away, and here, because it's the absolute value, it's going to look like the absolute value function, right? So it's going to look like this. And then for 2, if it's located here, L2, suppose L2 has a lower price, then it's going to be like here, right? But suppose it has the same price, right? So then here, and we will have the reservation value of the consumer that's located exactly at L2 minus the price of L2, right? And then here, the same transportation cost, so it's going to have like also like a B. Okay? And then here where the 2 cross, we're going to cross at L1 plus L2 over 2. And that's going to be a different consumer if the prices are the same.
The different consumer is the intersection, right?
The different consumers will be at the intersection here, right? So, given these utilities, right? Basically, these are going to buy from 1 and these are going to buy from 2, because for these consumers, this is higher. Oh, sorry. This is already like this is P1. This is like the total cost of buying from the firm. Sorry, it's not the utility. It's like minus AT. Okay? And we're gonna forget about the R because that's the same for everyone. So this is P2, right? This is P2, and then this is P1 plus the transportation cost. So this is P1 plus tau times x minus O1, right? And this is P2 plus tau times x minus O2, and on this side it's going to be what? Absolute value, right? It's like the total cost of buying from this firm and the total cost from buying from this firm. In both cases, you get the reservation value, the R, that cancels out, and then we have to compare which is more expensive for you, to pay P1 and then pay this transportation cost, or to pay P2 and then pay this transportation cost, right? So you're gonna buy from the one that's lower, right? So here, this is lower than this, and here, this is lower than this, okay? So all of the ones that are here buy from one, and this buy from two. And if I increase the price up to here, I'm going to get fewer consumers because now I'm going to be here, right? This is like P1 prime. And if I increase the price even more, then I get even fewer consumers. Right? So X hat starts shifting to the left. Is it right? Then the intersection moves to the left. So we have less demand and higher price. And the other one is more demand. Now suppose the other one lowers the price a lot. Right, all the way to like here. P2, right? So this is P2 prime, right? Much lower. At some point, if it keeps lowering the price, it's going to get to a point where the price is so low that everyone is at least indifferent to buying, at least everyone prefers buying from two, right? If the price is low, even these consumers now are indifferent between buying between P1 and P2, even though P2 is much further away, because P2 has a much lower price. But here's the thing that makes it badly behave. Because it's linear, now there isn't an intersection. Now, suddenly, when you go from here to here, it kind of like you capture all of the market. Okay, kind of like in homogeneous goods per tram. And so there's a discontinuity in the demand function with respect to the price of firm 2. With respect to, or with respect to the price of firm 1, if firm 1 is the one now that we're trying to lower the price to get the whole market. You see, I mean, there's going to be a point where you go from having up to here, and then suddenly you get all of them. Okay, there's going to be a jump in the demand function. You see what I mean? So this is going to, there's going to be a discontinuity in the demand functions. Because this is linear, right? So because it's linear, when I start moving this line here, it's going to overlap with this part of the V from the other firm. That's going to lead to discontinuity. Okay? This is going to be this model. This model is going to be not super well behaved. Okay, because there's going to be discontinuity. So it's not like it's impossible to solve it, but actually there's going to be no equilibrium in the supergame because of this, I think. But I think there is, it's like a mess to solve this.
Okay. Can you repeat the last part? Why is it discontinuous?
Why is it continuous? Because graphically, what happens is, as you move the price, there's a point where like you move the price down a tiny bit, and your demand jumps from like this much to everyone. Right? All of these people join from 2, all at the same time. Right? So an infinitesimal decrease in price leads to a finite discrete jump in the quantity value. You see what I mean? That's because of the linear, and that's because of the linearity of the transportation cost. So the model that's better behaved, and the model that we are going to try to solve, is Kotelin with quadratic transportation costs. Because the transportation costs are quadratic, then you don't have this problem, because you have quadratic functions instead of these b's. And the quadratic functions are always going to have like one point of intersection. I think today I'm gonna pose a problem set for you guys. Because there's like a whole week now, and now we've learned enough that we're ready to practice with some problems. So I think it's time for problem set 1. And then we can look at it next week, because Wednesday we will have class. Okay, so quadratic coupling. It's the same, but now V of V1 and V2 and V1 and V2 is equal, sorry, no, that's Vi is equal to the reservation utility minus Pi, minus the price, minus tau times x minus S squared. Okay? So now we're using the quadratic distance instead of the absolute value distance.
Sorry, Jose, it happened because of linear, did you say demand? Because of linear demand?
No, because of the linear transportation cost. That makes the demands discontinuous.
Vale.
Because basically what I'm doing is this, one of the V's is gonna at some point like exactly kind of overlap with part of the other V. You see what I mean? If I have these 2 V's, at some point this side of the V is going to touch all of the side of the other V, because they have the same slopes. This tau slope. You see what I mean? So that's annoying. So if I made it quadratic, then that doesn't happen. So the quadratic is going to be like this.
So that can never be.
So then this is always going to be fine, and there's no discontinuity. You eliminate the discontinuity in the demand.
Because the intersection is always going to be a point.
Because now the slopes are not constant. And the intersection of this is always going to be a point. So that's what we're going to quadratic column. And not the linear. Because now the demands are well behaved. Now what are going to be the demands? It's the same logic. We have to find the different consumer, which is the consumer, such that V1 of that consumer is equal to V2 of the consumer. But now we will have these quadratics. So we have to do basically P1 plus tau x minus 1 squared, which has to be equal to P2 plus tau times x minus 2 squared. So we have to expand this quadratic and solve for x, right? But because they're both multiplied by the same thing, and this is just like x multiplied by 1 here, the quadratic terms are going to cancel out. So I'm still going to get linear demands. Okay, let's see. P1 plus tau times x squared minus 2xL1 plus L1 squared is equal to P2 plus tau times x squared minus 2xL2 plus L2 squared plus L2 squared. The hard part cancels out. Otherwise, I would have had to use x equals minus 3 plus 1 over the square root. This thing. But I don't have to use it because this thing is cancelled out. Okay? Okay, now I do have to solve for x. Like before, right? So now I have P1 and P2, and let's do P2 minus P1. Here let's move like everything that has the x to this side. And here we're also going to have tau times L1 squared, P2 minus P1, plus tau times L2 squared minus L1 squared. And then tau times 2xL2, and then we have here minus tau times 2xL1, and then we have 2 tau on this side, tau times L2 minus L1 times x. Okay, so now to solve for x, I divide by this part, and then we have x hat is equal to P2 minus P1 divided by 2 tau L2 minus L1 plus tau times L2 square minus L1 square is L2 minus L1 times L2 plus L1. So this is going to be L2 plus L1 divided by 2 tau. It's not quite as nice as the linear one, linear Hotelling, but this is better behaved because the linear Hotelling actually doesn't apply. It becomes discontinuous at some point when the price is low enough. When the price differences are such that everyone is going to buy from one firm. And this is still Bertrand competition with differentiated goods and linear demands. So we have a constant is this, and then we have a slope 1 over tau, 1 over 2 tau times L2 minus L1. So now we have to solve for the what we have to do now. Backward induction. So first we're going to solve the pricing given the locations. There's no way we're going to be able to solve this problem in this class. Maybe I should just tell you the solution from the book. And we will add something else. Because this is like going to be like a wild amount of algebra or not that much payoff. Right? Don't be a hero.
Yeah.
But the algebra is not going to come in the exam? Because it's not, I think, better than theory. I speak for myself.
The algebra, I don't like using the Hotelling model for exams because there's too much algebra.
then we can change the solution.
So you can jump to something else.
So that's, but is it like the same result but with different transportation costs? That's basically it?
No, because now we can solve the super case, right? Before we could even solve, solve the game because the model was badly behaved. But now we can solve it. And so the idea is now to solve the price game, which is kind of like a triangle linear match just with this algebra. And then we have to substitute the prices in the profit function and solve for the optimal locations. Okay? Well, let's see. You know what? This year, I like going slow. I'm doing everything step by step and from first principle. So it's gonna be like it's in the book, but let's do it. No? I don't know. It's kind of. This is not gonna win the exam, instead of algebra, but it's informative and it's good practice to like solve the games and it helps us like see things. Do you guys? I mean, I don't know how to do algebra. I have to start doing it now. Do you guys want to see that? Yeah, you guys want to see it. I know. You want to see the struggle, sweating. I'm doing it. Fine, let's do it. We are the champions.
Yeah, we can put it.
We can put music to this.
Well, I was
Okay, let's do it. So, profits as a function of L1, L2, P1, and P2. Right? What are they? The profits are, let's say for firm 1. Let's say the marginal cost of production is symmetric and equal to 0. Just for simplicity, we're going to assume that C1 is equal to 0. We don't have to. But let's just make that easy. Okay? So then it's going to be the quantity x hat times P1. Right? And so the first order condition with respect to P1 for the second stage game. Remember, first we're doing the price game, and then we'll substitute the price in the profit, and then we'll solve for this. So for this game, we take the first condition with respect to price. And what is it? X hat. So this is going to be the derivative of x hat with respect to P1 times P1 plus x hat equals to 0. Okay? Can anyone tell me what the derivative of x hat with respect to P1 is the slope of this? It's going to be like minus 1 over 2 tau times h minus a1. Minus 1 over 2 tau times h minus a1
Yes.
times P1. P1 here. Plus x hat. X hat is that whole thing. So it's going to be P2 minus P1 over 2 tau times L2 minus L1 plus L2 plus L1 over 2 tau. This has to be equal to 0. And so that the best response function of firm 1, to get that we have to solve for P1 here. Did I do something wrong? It's like the P1 cancels out.
P1 cancels out, no? It's minus 2 P1, no? We have P2 over 2 tau, blah blah blah.
Maybe I can't assume that the marginal cost is 0. It should be also. No, it's here. Oh, no, yeah, you're right. No, it doesn't cancel out. No, it doesn't cancel out.
No, it's
Zero.
minus 2p1
It's minus
plus
2, right? So I'm gonna have minus 2p1, so I'm gonna put the p1 on this side. I'm gonna have p1
Or maybe it's just minus p1 over tau.
over 2 tau times L2 minus L1, right? Equal 2 p2 over 2 tau L2 minus L1 plus L2 plus L1 over 2 tau. But now we have to multiply this and we get p1 of p2.
But wouldn't it be 2p1?
See, it's,
Sorry?
Wouldn't it be 2p1 because it's minus p1 minus p1?
I think the 2 of the denominator goes.
Minus p1 over 2 tau.
Minus, and if you follow, minus p1 over 2 tau, so it should
No,
be.
Without the
Yeah, exactly.
And now, tau times L2 minus L1 is going to be P2 over 2 plus L1 plus L2 times L2 minus L1 is L2 squared minus L1 squared. The tau cancels with this tau over 2.
I have a question. At L2 and L1 over 2 tau, is it supposed to be 2 tau or no? The other equation. Yeah, it's supposed to be 2 tau over 2. It cancels out with a tau.
2 tau.
Because there's a tau before. So when you
There was a tau before.
at L2 plus L1.
Yeah, L2 plus L1 is multiplied by a tau. Is in between parentheses multiplied by a tau.
Oh. Oh.
So yeah, basically that goes, yeah.
Oh. Ah. So there's no tau here. And then there's no tau here. And then this one
You should
have
stay
a tau.
without the squares, no?
times tau.
Oh. Ah, yeah.
Okay, so now we this is the best response of from 1 or from 2. Now I could calculate, since the forms are symmetric, I could calculate a symmetric Nash equilibrium for the pricing game. Yeah, I can do that. No, I can't. I can't. Think about it. This is more important than solving the model and all the algebra. The firms are going to play a game first in locations. First stage, location. Second stage, price. What happens if in the first stage I say they're symmetric? I just calculate the symmetric price equilibrium. Does that work? For solving the super game?
Yes.
For solving the super game?
Can you repeat again? If you solve
If I solve for this, now I can say, okay, P1 equals P2. I mean, imagine I did this. No. If I said, okay, therefore, Nash equilibrium symmetric firms,
Yeah.
P1 equals P2, P equals P2, P equals P over 2 plus L square, L2 square minus L1 square over 2 times tau, and therefore I just pass this here, that's
Here.
the next 1/2, and therefore P star is equal to L square minus L1 square
times
is
tau.
equal to 1/2 times tau. What if I do that? Would that be wrong? That would be totally wrong. Because the forms are symmetric ex ante in the first stage. But in the second stage, they're no longer symmetric because L2 is not the same as L1. L2 and L1 could be anything, and I have to consider anything that could happen between L2 and L1. And I have to consider everything. I cannot impose symmetry in the locations in the second stage. Because if I did, then how the hell am I gonna, excuse me, and probably we're in a Catholic school. And then how in the heavens am I going to be able to calculate the first order condition with respect to locations? Because the first order condition with respect to location is assuming a location for the other firm, right? Which could be the same as yours, but then like you have to consider fixing that and modifying your location. You see what I mean? So you have to be able to at least consider what would happen in asymmetric location scenarios. You see what I mean? And what would happen to prices in those scenarios in the second stage. You see what I mean? So I cannot do this. No. Can't do it. I have to solve for the asymmetric equilibrium in prices. Okay, so I need to solve the 2 by 2 systems of P1 and P2. Okay, so basically I've solved for P1, P2 is going to be the same, but the other way around. I put it right up. I have to figure out, let's do the first condition for firm 2. Okay, so demand for firm 2 is going to be 1 minus that. Okay, so demand for firm 2 is 1 minus x hat is equal to 1 minus P2 minus P1 over 2 tau times N2 minus L1. So this is the same as like I do this. Now it has a plus. P1 minus P2. Okay, so that's going to be the same. And then I'm going to have plus 1 minus L2 plus L1 over 2. So it's 1 minus those two things here. 1 minus P2 minus P1. So I get 1. The 1 I'm going to put it, it's going to be 1 minus L2 plus L1 over 2 plus P1 minus P2 over 2 tau times L2 minus L1. So now I have this L minus PQ. Okay. And now the first order condition is going to be, okay, the derivative of this with respect to P1, with respect to P2, sorry, is going to be minus P2 over 2 tau times N2 minus L1 plus P1 minus P2 over 2 tau times L2 minus L1 plus 1 minus L2 minus L1 over 2 equal to 0. Now I have the P2 there, right? And I'm gonna have P1. One is gonna look very similar. So I'm gonna have P1.
But you have the same denominator in those two, can't you add them up and the P2 goes away?
We're gonna have P2 over 2 tau times L2 minus L1 equal 1 minus L2 plus L1 over 2 yeah, P2. Oh no, wait, I moved the P2 to the other side. And it's 2 P2, so this goes away. And this is going to be equal to L2 plus L1. Let me do it this way. 2 minus L2, 2 minus L1 minus L2 over 2 over there. This will be 1 minus this plus V1 over 2 tau and 2 minus L1. Okay, and now I have to pass this that way. And this 1 minus, I already put that. So now it's going to be P2, this response, P2 as a function of P1 is going to be equal to tau times L2 minus L1, and it's going to be P1 over 2 plus tau times 2 minus L1 minus L2 times L2 minus L1 divided by 2. Here it doesn't look as nice as that because it doesn't have the square. But, we could express it in terms of the square here by doing L1 minus L1, 1 minus L2, and this is 1 minus L2 minus 1 minus L1, and the ones cancelled out. Right, so this is the same as 1 minus one minus L1 squared minus 1 minus L2 squared over 2. Okay? So there is some symmetry. You see what I mean? 2 minus L1 minus L2 times L2 minus L1 is 1 minus L1 squared minus 1 minus L2 squared. I'm dividing these two, I'm doing 1 minus L1 and 1 minus L2, right? So this is 1 minus L1 plus 1 minus L2 plus 1 minus L2, right? And here I have 1 minus L1 minus 1 minus L2, right? And the ones cancelled out, and this minus became a plus and became L2. And so now this is like L1 tilde plus L2 tilde times L1 tilde minus L2 tilde. And that's L1 tilde squared minus L2 tilde squared, or 1 minus L1 squared minus 1 minus L2 squared. So we're not going crazy here. Things are symmetric. It is the same as if I called the location, I flip the locations and I call L1 1 minus L1 tilde, and so on. So, okay. Now that we have this, now we have to solve it. So now we have to substitute that P1 here. So we have P2 is equal to P2 over 2 plus L2 squared minus L1 squared over 2 times tau divided by 2 plus tau times 2 1 minus L1 squared minus 1 minus L2 squared. And I have this P2 here over 4, passes to this side, and I have 3/4, right, times P2. That's going to be 4/3 times whatever's left here that didn't have a P2. So P2 star is going to be equal to 4/3 times L2 squared minus L1 squared over 4 times tau plus, or you could say that the tau oh no, because the tau came back because of this, plus tau times 1 minus L1 squared minus 1 minus L2 squared over 2. The 4 here cancels out. The tau maybe could come out. So we're like tau P2 star is equal to tau times L2 squared minus L1 squared over 3. Oh, this is also times 4/3. Here the 4 becomes a 2 and this 2 also. So I will have a third there too, so it could also bring the tau over 3 out. And with tau over 3 times L2 squared minus L1 squared plus 2 times 1 minus L1 squared minus 1 minus L2 squared. Okay, so that's the price of 2. The price of 1 is going to be analogous, not symmetric. So we tie over 3 times L1 squared minus L2 squared plus 2 times 1 minus L1 1 minus L2 squared minus 1 minus L1 squared. Is that correct? Probably not. I think it's better to actually substitute this into the other one. Not go too fast here. Okay, this one is P2 star. Now, we can probably simplify this.
Yeah, we
Yes, we can. No, Obama again. It's like, I thought he left a long ago. You know, I was listening to this, The Oceans. But on Netflix, there's like this thing that talks about like the oceans, like this sort of kind of National Geographic kind of thing. And I was like, that voice sounds familiar. And it says, narrated by Barack Obama. So now he's like this like voice for like this like nature documentaries in Netflix. It's weird. Okay, L2 squared minus L1 squared plus 2 times, and now we have to expand these squares, right? Yeah, so basically 1 minus 2 L1 plus L1 squared minus 1 plus 2 L2 minus L2 squared, right? And all these multiply times 2. The 1 cancels out. And we are left with minus 2L1 plus 2L2 plus L1 squared minus L2 squared. But this is times 2. So this is really minus 4 plus 2L1 squared plus 4 minus 2L2 squared. And so we have L2 squared minus 2 L2 squared is minus L2 squared minus L1 squared plus 2 L1 squared, that's going to be L1 squared.
Yeah, so it's 1 squared minus 4L1
L1 squared
minus 4L1
minus 4 L1 minus L2.
exactly minus L2 plus 4L2.
So minus 4 L1 minus L2, that would be like, let's say this is L1 squared plus 4 times L2 minus L1. In general, as a convention, I'm going to think of L2 as the one that's above L1 minus
L2 squared.
minus L2 squared. Okay. So now it's L1 squared minus L2 squared plus 4 L2 minus L1. Let's see if we can simplify that even more. This model is not super well here.
Use either before the rest.
No, this one is.
Ah.
I was just reading the resolution. So P2 star is equal to tau over 3 times L1 squared minus L2 squared plus 4 times L2 minus L1. And now, what if we write this L1 squared minus L2 squared as L1 minus L2 times L1 plus L2? This way. Then we could take out common factor L2 minus L1. So then it would be P2 star is equal to tau times L2 minus L1 over 3 times L1 minus L1 minus L2 4 minus L1 minus L2. This looks nice, I think. Okay, now we have to substitute this into the response function for from 1. If you want to be really careful. Okay, so P1 of P1 star, P2 star, P1, also P1 star, is going to be equal to this substituted there in the base response function. So it's going to be this over 2. So it's going to be tau times L2 minus L1 over 6 times 4 minus L1 minus L2 plus L2 plus L1 over 2. Is that it? No. L2 squared minus L1 squared over 2. Okay, L2 squared minus L1 squared over 2 is equal to L2 minus L1 times L2 plus L1. And there was no tau here?
I was just about to ask that if we need to put times tau or not times tau.
Yeah, we should know.
Oh, there's a tau. There is a tau. Yeah, times tau, times tau. Otherwise we'll be in big trouble. Okay? So yeah, times tau and this over 2. Okay, so now we have tau over 2 times L2 minus L1. And here we have tau over 6, which is like tau over 2 times L times 3, right? So now this to convert it into a 6, we multiply this times 3, right? So we have like over 6 times 3. And now we can put it in here. So this is going to be equal to tau over 6 times L2 minus L1 times 4 minus L1 minus L2 plus
3.
3L2 plus 3L1.
And now we simply remove this 4 plus 2L2 plus 2L1.
4 plus 2 times L2 plus 2 times L1. And now we can take the 2 out, and we're going to get 2, right? And then the 2 cancels with the 6, and so it's going to be equal to tau
Tau over 3.
over 3 times L2 minus L1 times
2 minus L2 plus L2 plus L1.
2 plus L2 plus L1. 4 minus L1 minus L2, 2 plus L2 plus L1. Oh, we could have written this as 2 plus 1 minus L1 plus 1 minus L2. So they're kind of symmetric in a way. Not symmetric, but analogous, right? Just one is in terms of L1 and L2, and the one in terms of 1 minus L1 minus L2. Okay, this looks great. So now I have the prices in the asymmetric second stage equilibrium. You see what I mean? This I could have thought of as 2 plus 1 minus L1 plus 1 minus L2, and that's very similar to 2 plus L2 plus L1. But now, that's not enough, because now I have to substitute these prices into the profit functions. And then I have to take first order condition with respect to the location. Okay, so now I have to substitute the prices P1 star and P2 star into the profit functions. The profit function, though, is easy because we set the marginal cost. We simplify by setting them equal to 0 to simplify the algebra. So it's just the price and the quantity. But now we need to solve for the quantities, and then we have the profits, right? So what's going to be the quantity? What's going to be x hat of P1 star and P2 star? Is going to be equal to, it's over there, right? It's P2 minus P1 divided by 2 tau times L2 minus L1 plus L2 plus L1 over 2. So it's going to be L1 plus L2 over 2 plus the difference between these two over 2 tau L2 minus L1. 1 over 2 tau times L2 minus L1 times the difference between P2, which is 4 minus L1 minus L2 minus 2 minus L2 minus L1, right? Right? Minus 2 plus L2 plus L1 times tau times L2 minus L1 over 3. This is 4 minus 2 is 2, minus L1 minus L1 minus 2L1 minus 2L2, so this is just 2 times 1 minus L1 minus L2, I believe. This 2 is going to cancel with this 2. This tau is going to cancel with this tau. L2 minus L1 cancels with L2 minus L1. So then 1/3 times this. So it is equal to 1, it is equal to L1 plus L2 over 2 plus 1 minus L1 minus L2 over 3. This is the quantity, right? And then the profits from 1 as a function of L1 and L2 are equal to this times the price of it. The price of 1, right, which is this. So it's going to be equal to the quantity, which is L1 plus L2 over 2 plus 1 minus L1 minus L2 over 3 times price T times tau times L2 minus L1 over 3 times 2 plus L1 plus L2. So that's the objective function from 1 for the first stage of the Super Bowl. The Super Game. Okay, I'm trying to, keep composure here after 3 hours of suffering. Hakuna Matata.
Vale.
Okay. And then we're going to have to do something similar from 2, right? Now we have to,
But x hat is the same, no?
no, we have for film choice, I mean, 1
It's
minus.
1 minus x hat.
Exactly.
Yeah, but we also have it somewhere, yeah.
I mean, well, let's think about it this way. It's like, it has to be analogous, right? It has to be, phi 2 has to be, if they chose the locations but they switch them, the profits
Yeah.
would just be switched, right? So it has to be pi 2 of L2 and L1 has to be equal to L1 plus L2 over 2 plus 1 minus L1 minus L2 over 3. So far everything's symmetric actually. Times tau times L1 minus L2 over 3. This is present to see. No, plus L1 plus L2. This might be because I'm assuming that from 2 is the one that's higher actually. So I'd have to substitute. But let's see what the first order condition would look like for from 1. What's the derivative of I1 with respect to L1? It's going to be equal to it's the derivative of this times this plus can we simplify this further? Maybe not, right? The derivative of this with respect to 1 is 1/2 minus 1/3. 1/2 minus 1/3 times this thing here, which is positive, plus this times the derivative of this, which is tau over 3 times the derivative of this times this, which is minus 1 minus 2 minus L1 minus L2 plus this L2 minus L1 times the derivative of this, which is 1. Okay, and then L2 and minus L2, this cancels out. So we have minus 2 times minus L1 minus 2 times 1 minus. This is negative. 0. Okay, we're out of time.
Yeah.
Think about whether we can simplify this profit function.
Jose, what, your parentheses that have a point inside, what do they refer to?
Well, this is like this sort of thing here. I put like points, right? This whole thing here. That's because it's like the derivative of a product. I mean, I have one of it. But actually, I think a better approach to thinking of this derivative is to try to simplify this. I think this can be simplified.
Yeah, that for sure has to be able to.
This for sure. Actually, the book gives you a simplified expression for this that looks pretty nice.
There are too many L1s and L2s.
This has to do
This is part 3,
we
right?
didn't
The
read-
how to read more like
yeah, this is in chapter 5.
Chapter 5, but it's part 3.
5.
We've done part 1,
Yeah,
part 2.
actually, the book
10.
says that the profits
10.
from 1 are 1
Chapter
over
11,
18 times tau times L2 minus L1 times 2 plus L1 plus L2 squared. So if we start simplifying, no,
Xiaomi, you have Xiaomi.
Uy, el segundo partido 18, que feo, ¿eh?
O sea, esto es con time annotation.
O sea, el segundo partido con 18, eso hace llorar al niño Jesús, ¿eh?
Bueno, es 1 sobre 3 y un medio.
Sí.
O sea, es porque ya tenemos un medio, un tercio, ¿no? 6 por 6. Acá tenemos un tercio. Multiplicas, va a dar.
Le explico yo acá para que vaya poniendo en el calendario los santos, parece.